We all remember this from algebra class, right? A plus b to the power of 2. That's easy, we just use FOIL to expand it. So a times a is a squared, plus a times b is ab, and then a times b is also ab, and then b times b is b squared. So we get the final result of a squared plus 2ab plus b squared. And it works. But what if our exponent is in the 10s, in the 20s, in the 30s? What if our exponent is negative, say 1 over a plus b to the power of 2? That means that, of course, our exponent is actually negative 2. So how do you do that? And what if we use Pascal's triangle? Of course, Pascal's triangle is true and it works, but it only works for natural numbers or positive non-zero numbers. Again, what if the exponent is negative or a fraction? And that's where the binomial expansion comes in. But before I explain to you what the binomial expansion really is, I want to explain to you the pattern behind the binomial expansion. So when we have a plus b raised to the power of n, we have actually quite a unique pattern. So we have a plus b to the power of 1, of course it's just a plus b, but when we add a plus b to the power of 2, we can see that for the first term we have a squared. Now on the second term, the exponent of a it actually decreases by 1, and for the third term, the exponent of a is actually 0. So if you see the pattern, the exponent of a is actually decreasing 1 by 1 until it reaches 0. So it starts off from a squared to a power of 1 and then a to the power of 0. And then we see the same thing in b. For the first term, we start off as b to the power of 0, and then on the second term, we have b to the power of 1, and then on the third term, we have b to the power of 2. So we can see that for the exponents of a, it always decreases 1 by 1 until it reaches 0. And then for the exponent of b, it always increases 1 by 1 until it reaches n. This pattern is also seen more clearly in a plus b to the power of 3. On the first term, we have a to the power of 3. And then on the second term, we have a to the power of 2. It reduces by 1, right? And then on the third term, we have a to the power of 1. And then on the final term, we have a to the power of 0, or just 1. And that's hence why we don't write it. And then on the b, it's also the same thing. On the first term, we start off with b to the power of 0. And on the second term, we start off with b to the power of 1. And then on the third term, we continue with b to the power of 2. And then on the last term, we have b to the power of 3. So the pattern is that for any a and any b, the exponent is actually increasing and decreasing until it reaches n and until it reaches 0. So for the binomial expansion, it looks something like this. It might seem a little intimidating, but if you grasp the core concepts, it's actually really easy. And compared to multiplying or foiling, just complicated, right? So when we have a plus b to the power of n, we have n choose 0 or for the coefficient, and times a to the power of n times b to the power of 0. So when we have a plus b to the power of 2, we actually have 2 choose 0 times a to the power of n, which is 2, right? Times b to the power of 0, because it starts off at 0. And then plus 2 to the power of 1, because the k always increases, right? 2 choose 1, not power, sorry, times a to the power of 1, because the exponent of a always decreases by 1 until it reaches 0, and then times b to the power of 1, and then plus 2 choose 2 or n choose n. So the final term is actually n choose n times a to the power of 0 times b to the power of n. This is the final term. Now for the final term, we have 2 choose 2 times a to the power of 0 times b to the power of 2. So 2 choose 0 is just 1, right? 1 times a squared, so that's basically just a squared, plus 2 choose 1 is just 2 for the coefficient, and then a times b, so ab, plus 2 choose 2 is 1, and then a to the power of 0 is also 1, so we only have b squared. See, it's the exact same thing as this, but we use a much faster method, especially for exponents above 10 or 5, where foiling just really becomes ineffective. So this is the base form of the binomial expansion. Of course, it may look intimidating again, but it's actually really simple. This symbol right here just symbolizes that you just sum everything, right? And then this just combination formula of n choose k for the coefficient. And then here we have a to the power of n minus k and b to the power of k. I like to think of this as a forward and backward motion, like in chemistry. The exponent of b always increases from 0 to 1 to 2 to 3 all the way until it reaches n. And the exponent of a always decreases from n to n minus 1 to n minus 2 all the way until it reaches 0. So let's jump straight ahead to the exercise. So here we have x plus 2 to the power of 6. Now for the first term, again from the example above, we have 6, or n choose 0, because the n is equal to 6, right? So 6 choose 0 times x to the power of n, which is 6, times 2 to the power of 0. Now for the second term, we have 6 choose 1, because the k is always increasing, and choose k, and then times x to the power of 5 times 2 to the power of 1. So the exponent of 2 is always increasing because it's b, and the exponent of x is always decreasing until it reaches 0. And then for the third term, we have 6 choose 2 times x to the power of 4 times 2 to the power of 2 plus, again, we just repeat this pattern over and over, 6 choose 3 times x to the power of 3 times 2 to the power of 3 plus 6 choose 4 times x to the power of 2 times 2 to the power of 4. Now we have for the fifth term, we have 6 choose 5 times x to the power of 1 times 2 to the power of 5, and then for the final term, we have 6 choose 6 times x to the power of 0, or just 1, times 2 to the power of 6. But this is the full expanded version of x plus 2 to the power of 6. This is way easier than just multiplying the terms one by one. And so when we simplify this, 6 choose 0 is just, it's 1, times 6 x to the power of 6. So we have, for the first term, x to the power of 6 plus 6 choose 1 is just 6, if I remember. 6 times 2 to the power of 1, or 2. So 6 times 2 is 12. So 12 times x to the power of 5. For the third term, we have 6 choose 2, it's 15. 15 times 2 to the power of 2 is 4. So 15 times 4 is 60. So we have 60 x to the power of 4. And then on the fourth term, we have 6 choose 3, which is 20, and 20 times 2 to the power of 3, which is 8. So we have 160 times x to the power of 3. And on the fifth term, we have 6 choose 4, which is 15, and then times 2 to the power of 4, 16. So 15 times 16 is 240. 240x squared. And then on the sixth term, we have 6 choose 5, which is 6, and then times 2 to the power of 5, which is 32. So 32 times 6 is 192 times x to the power of 1, or just x. And then on the final term we have 6 choose 6, which is just 1, and then times x to the power of 0, which is just also 1, and then 2 to the power of 6, which is just 64. So this is the fully expanded version of x plus 2 to the power of 6. Of course, it's really simple other than just foiling or just using Pascal's triangle. So now we have expanded and used the binomial expansion to expand a binomial to the power of n over than 2 or 3. Now I have an exercise for you guys. So I have two questions. One is easy, one is hard. So medium. So for the easy one, we just have x plus 1 to the power of 4, and then for the medium one, we have 2x plus 3 to the power of 4. Now on the next video, I'll cover the exponents when the exponents are negative, as for example here is 1 over 2x plus 3 to the power of 3, which is just basically 2x plus 3 to the power of negative 2, and even square roots. So maybe 2x plus 3 over the root of maybe x plus 1. As we all know, the root is just the exponent of a fraction. So in the next video I'll cover about this. So that's the end of part 1, where we discussed about the fundamentals of binomial expansion. If you enjoyed my videos and found them useful, please subscribe to my channel and share your videos, my videos to maybe your relative, your aunt, your uncle, whatever. And on the next part, I'll discuss about this, where our exponent is negative or a fraction. Bye everyone, thank you.